All right, mathletes, here we are looking at graphs of exponential functions. What are exponential functions? Well, those functions are going to have this format, f of x equals b of x, where b is any positive real number. We know we call this an exponential because the exponent x, and we have a base of a power b, which is called our base. Okay, so where do we see exponential functions? We see them in a variety of places, a lot with investments and looking at interest calculations, whether it's interest being applied to mortgages or loans or credit cards that we take out, or applied to investments in savings accounts or things of that nature. We look at population growth, whether it's people, bacteria, or animal population. Newton's laws of cooling involves exponential function, and also radioactive decay, measuring half-lives and calculating how old things might be. So let's look at our first example of graphs here. So our first example is f of x equals 2x. So first thing we want to do with graphing, we're just going to plug in some tables and get some idea of what's happening. So let's do it here at -2, -1, 0, 1, 2, and 3. And then from there, so if I plug in -2 into the exponent here, okay, I get 2 to the -2nd is going to be 1/4. Remember, negatives drop things into the denominator, so then we get 1/2 for -1. Anything to the 0 power is 1. 2 to the first is 2, 4, and 8. So as I graph those, I'm going to see at -2, I get -1/4, so about there. At -1, I get 1/2, so about there. 0, I'm 1. At 1, I'm 2. At 2, I'm 4. And at 3, I am 8. Okay, so you end up getting this function. We'll talk about, we have a horizontal asymptote, because nothing raised to the second power is ever going to go less than 0. So this function is never going to be, oh, I have that wrong there, but that this function will always be greater than 0. So that means we always will have this horizontal asymptote at y equals 0 for our parent function. Okay, so that will help us as we start talking about our domain range of these things. So our domain for an exponential function is going to just be for all real x's. Okay, the range, again, we can't go negative here, so this is range, so we want to say for all real y's such that y is greater than 0. Okay, the second piece is our y-intercept. Our y-intercept is, since any exponent to the power of 0 for our parent function is always going to be 1, whether that base, doesn't really matter what that base is, it's always going to be 1 to the 0, because anything to the 0 power is 1. Okay, is this a increasing or decreasing function? Well, this is increasing. We can see it's going uphill as we move from right to left, and as we stated before, our horizontal asymptote is y equals 0. Okay, so that's our first graph that we're going to look at. Let's look at another one here. So our second graph is, now notice our base is 1/2, so it's a fraction. It's less than 1. So the first thing we are going to do is, again, graph some points here. So I get -3, I get -2, -1, and 0, 1, and 2. So as I put in -3, remember that's going to flip my fraction, so that's really just 2 to the 8th, which is 8. Then 2 squared is 4. 2 to the first is going to be 2. Anything to the 0 power is 1. And then to the 1/2, so it's itself. And when it's squared, it's to the 1/4. That looks kind of flipped from our previous one, because remember, we can write this as 2 to the -x. With this -x there, what we really see is a reflection across our y-axis. So let's go ahead and graph these x and y points. Okay, so at -3, I have 8. At -2, I have 4. At -1, I have 2. At 0, I have 1. And then 1/2 and 1/4. So as I graph this function, it's going to look something like this. It's going to get closer and closer to 0, or this asymptote here. It's close. Getting used to this new note-taking format. But we see that our horizontal asymptote is y equals 0 again. So our domain, again, is going to stay for all real x's. Okay, our range is going to be for all real y's, such that our y's need to be greater than 0. Okay, our y-intercept, again, is at 0, 1. And this is a decreasing graph. Okay, we'll notice when we have this b value here, that is that 1/2. When that is less than 1, we'll have a decreasing graph. When it's greater than 1, it's going to be an increasing graph. So let's look at another example here. So on 3, we're looking at an exponent that has a little adjustment here. So think about our transformations that we've done on other functions before. Let's start off by graphing and calculating some coordinates. Okay, so when x is 5, okay, 5 minus 3 is 2, 2 squared is 4. X to the 4th, that's 2 to the 1st, so that's just 2. 3, that goes to 0 in our exponent. Anything to the 0 power is 1. 2 is -1, so a negative power is going to flip it. And then to the first power here, I'm going to get 1/4. So as I graph this, I get 5, 4. I get 4, 2. I get 3, 1. At 2, I'm 1/2. And at 1, I'm 1/4. So as we look at this, we see it's similar to our x to the negative x graph, but we have a horizontal shift happening here. So our domain, even though we're shifting it left and right, our domain is going to stay consistent for all real x's. Our range is going to stay consistent because we haven't shifted up or down. So it's for all real y's such that y is greater than 0, not equal to 0. Our y-intercept, so our y-intercept on this one, so if we let this, if we put in a 0 there for x, okay, 2 to the -3rd power, well, 2 to the 3rd is 1/8, and a -1 is going to drop it in our denominator, so that's 1/8 here, so we're really close down there. So we are 0, 1/8. Okay, we see that this is a decreasing function. Okay. Oh, I'm sorry, it's not decreasing, it's just a shifted over graph, so it's increasing. It's increasing because we see this 2 is a larger than our 1, and as we go from left to right, it's increasing. Our horizontal asymptote stayed at y equals 0. Looking at our final example of graphs here, we have a couple other things going on. We have an 8 minus 2 to the x plus 1. So let's graph some points here in our table. So there's our x and our y. Points I'm going to use are going to be 2, 1, 0, -1, and -2. So I plug in 0 there. I get, when I plug in 2 here, I get 2 to the 3rd. And 2 to the 3rd is 8. 8 minus 8 is 0. Okay, so I get 1. When I put 1 in there, I get to the 2 squared. 8 minus 4 is 4. Plug in 0. It's going to be 2. 8 minus 2 is 6. -1 is going to be 7. And at -2, I get 7.5. Okay, so as I graph that, at 2, I'm 0. At 1, I'm 4. Okay, at 0, I'm at 6. Okay. And as I'm at -1, I'm 7. And at -2, I'm 7.5. Okay, so what we end up seeing here is we have a reflection. Almost got all those points. Okay, of our exponential function vertically. It's a vertical flip, and that's dictated by that -2 there. And then we have a vertical shift where this 8 shifted our graph up 8, and that +1 there looks like we shifted over our graph to the right 1. So our domain is going to stay consistent here. It's for all real x's, but our range changes here. So for all real y's, such that, well, we have a horizontal asymptote here as this graph. Okay, it's going to be there. So then we know that our y is going to be less than 8. Our y-intercept we can see is 6, so we get 0, 6, and this is a decreasing graph. And our horizontal asymptote was there at y equals 8. Okay, let's look at some other concepts here. So as we're talking about graphing function exploration, okay, how do we know what A, B, H, and K affect our graph? Well, we should notice that our A value, okay, if our A is negative, so if that A value is negative, okay, that we saw in our last one, we had a -2, okay, that's a negative, it's a vertical reflection. Okay, we'll notice our K value is outside of our X, and similar to our other kinds of transformations, that's going to be a vertical shift. Okay, our H value, that negative in there reminds us that it's kind of opposite of what we think. That H is a horizontal shift. Where if we see like a +2 in there, the H is a -2, which is going to make it a shift in the left direction when it's positive, when it's negative. So when it's positive, it's a shift left. And when it's negative, it's a shift right. Okay. So determine it if we're given a set of numbers and we want to determine if it's an exponential function, what we want to do is be able to identify the base, meaning there is a common ratio. So what I want to do is just double check and make sure that I have common indexing here. So since that indexing is common, it's going up by +1 each time, it's a common indexing. So then I can look at the table of values and see if there's a common ratio on this side of my output of my y's, or my f of x's. So if I look at these and I see that 27/9 is equal to 9/3, which is equal to 3/1, which is equal to 1/1/3. These all simplify most simply to this ratio here, which is 3/1. So that's our common ratio. That's going to force us, that common ratio is our base A. So if we have our equation, we're thinking of it as y equals, or f of x equals 3 to the x. Okay. So if we look at our next one, again, we notice common indexing here. We get a +1. So we look at our common ratios. We get 4/2. Is that equal to 2/1? Or 1/1/2? Or 1/2 over 1/4? Let's double check this with fractions. That's a little complicated. So dividing by something is the same thing as multiplying by the reciprocal. So 1, and we see that that's 2/1. And that's common for all of these here. So that means our common ratio is 2 over 1. So if we wrote this function out, we would identify this as an exponential function with a base of 2x. Okay. The last thing we want to look at is to be able to identify those transformations looking at our graph here. So with a +1 on the numerator, I'm going to notice that that's a left. So that's a left 1 transformation. A -4, that's a vertical flip with a negative in front of that value. So here we got two transformations happening. That right there is going to move us right 3. And here is going to go up 5. Okay. When we're dividing here and we have x, this is a vertical compression. And then here, so we have a 5 here, so that's a vertical stretch. And a negative up here, okay, is going to be a flip, but in the horizontal direction. Okay, that concludes our notes tonight, mathletes. Go ahead and highlight any questions and bring them to class tomorrow.